Thank you for coming to Theory Lunch. Today we have Jason, who will talk to us about deterministic path decomposition and negative weight shortest paths.
Thanks, Andreas. Okay, so let's get started. So in this talk, we'll look at the single source shortest path problem, the classic problem of combinatorial optimization. So given a source vertex called S, you want to find the S to V shortest path, let's say just distance for now, the weight of the shortest path from S to all other vertices V. And a classic result from undergrad algorithms is that when the graph has non-negative weight edges, then Dijkstra's algorithm essentially is near optimal. It's m plus n log n, so within a log factor of optimal. And there's been some recent breakthroughs, which I will not touch on this talk, that actually improve upon the log factor. And in fact, the message is like you can solve negative weight shortest, non-negative weight shortest paths faster than sorting the list of numbers. But in this talk, we'll mainly focus on the presence of negative weights. So it's well known that if negative weights appear, then Dijkstra's algorithm, you think of as a greedy algorithm, it just greedily finds the smallest unvisited distance. This greedy algorithm fails, and therefore the running time is probably remain open for a long time. So the previous state of the art before this recent line of breakthroughs is by Goldberg. He got an m root n, again without log factors. But this is for the setting of integral weights. So this is the setting when weights are integral and all weights are at least minus w, or some w. So there's no bound on the positive weights. Turns out that's very large positive weights do not really affect this algorithm, but very large negative weights do. And this remains the state of the art until a very recent breakthrough, about 4 years ago. Bernstein, Nanongkai, and Wulff-Nilsen obtained essentially a near linear kind of algorithm. Once again, for the setting where the edges are integral and have weight at least minus w. Okay, so this BNW algorithm can be thought of as a more modern approach to graph algorithms. It combines some old techniques such as potential functions and divide and conquer with some more modern techniques such as graph decompositions, and which we'll see a bit more later. But these are the graph decomposition used for in this result was randomized, and our main focus will be de-randomizing it, or having a deterministic analog of this algorithm, which is also arguably similar. Any questions so far? Okay, so let's begin with, so I'll essentially discuss the list of techniques that was used in previous work, and then later on I'll pivot to what is a deterministic analog of this graph decomposition. Okay, so let's begin with potential functions. Okay, so a potential function is essentially a function on the vertices. So it assigns every vertex a real number. Because in the case of integers, you can think of them as integers. Every vertex gets an integer. And the role of a potential function is to reweight the edges of the graph. So recall this is an edge-weighted graph. And every edge will have a new weight equal to the old weight. So this is the new weight under the potential function equals old weight plus the tail of the vertex minus the potential of the head of the vertex. So this is a directed graph. Edge weights are defined this way, where of course directions matter because UV is an edge from U to V. So now let's see what is the role of this reweighting for a given path. So let's say we have a path. We have S on one and T on the other end. And the old weights are just like the old weights without these plus or minuses. But let's see what is the role of this reweighting on this path itself. Okay? So note that, for example, this edge has now weight, the old weight plus 5s minus 5u. This edge has similarly plus 5u minus 5v and so on. And now the observation is that, so why is this potential function useful? It's because there's a telescoping going on. So if you sum up these quantities over an entire path, everything telescopes, these cancel. The only surviving terms are plus phi s minus phi t and the origin weights themselves. So what does this mean? This means that the total weight is just the old weight. This is just the old weight plus phi s minus phi t. So what does this mean? That if you fix s and t, so let's say you fix s and t and you look at maybe let's think about what is the shortest SD path. Well, it turns out since every single SD path is offset by the same amount, depending only on S and T, that means that the shortest path after reweighting is still the shortest path before reweighting. Okay. So this is why this potential is useful, and in fact, pretty much universal in all modern, recent negatively shortest path algorithms. Is the fact that shortest paths are preserved. You fix S and T as endpoints, all paths get offset by the same additive amount, and therefore shortest path is still shortest paths. What does that mean? That means that if you reweight the graph and compute shortest paths, there's still shortest paths in the original graph. All you do is offset by this plus S minus 1. Any questions so far? So this was a classic. This was a result by Johnson from the 1970s. He used this to solve, for example, all pair shortest paths even on negative weight graphs. Because this technique works for all pairs. This S and T are arbitrary. But this talk will be used to solve a single source with negative weights. Okay, so let's just to understand this potential function better, let's prove some like simple claims. The first claim is, suppose we set the potential function to just be the shortest path to V. And here I'm going to be like, you might ask, well, shortest path from which vertex? I'm going to be a little more general in this setting, where I'll say this is the shortest path starting from anywhere to V. We'll show later on this is kind of like morally the same as single to shortest paths, but for now just assume that that's defined to be the length of the shortest path to V starting from anywhere. So for example, the empty path starting at V to V is the valid shortest path. So in particular, this path, if it's better than that, must be negative. This will be a fact we will use, but for now, we will not really use that much. Okay, so the claim is that under this reweighting, all edges automatically become non-negative. So even if they were initially negative, after this reweighting, all edges become non-negative. And what is the proof? So recall the definition. This is just by definition. And the only fact we'll use the triangle inequality. So for any, so I claim this is true. Why is that? So this is the short distance to V, starting from anywhere. What is a valid way of forming such a path? You take the shortest path to U, wherever it is, starts, and then add on the edge UV. This will be a path that goes to U and then ends at V, takes one step to V. This is a valid path ending at V, and this is only the shortest path. So this non-negative inequality holds. And this is known as a triangle inequality. This holds for any distance, any metric. And if you rearrange, you will get essentially. So any questions? Okay, so what is nice about this reweighting? Well, suppose you have this reweighting, then because all edges are non-negative, you can just apply extra. Right? And recall that potential functions preserve shortest paths, so these shortest paths will become original shortest paths once you remove the offsets. Okay? But of course, the issue is that this already requires the shortest path call. And in fact, it's actually equivalent to single to shortest path, so here's the construction. So why is this essentially single to shortest path? You can add a new source vertex, connect this vertex with edges of weight 0 to everyone else. Right? Then that means that starting from anywhere, and any at B, it's just the same as starting from S, taking a 0 weight path edge to that vertex, starting vertex, and then going to V. That's the same distance. So it turns out this is really about single to shortest paths, but turns out this, starting from anywhere, this enforces all paths to be 0 or smaller, like negative or 0. This will be useful. That's why I use this. Okay. Okay. So in other words, maybe this function is too much to hope for because finding this function immediately already requires single shortest paths, which we don't have. So here's the first idea behind this B and W algorithm. So this is actually a new idea. Is let's kind of gradually find a good potential function. So consider the following setting. So recall G is the original graph. Let's define G prime to be the graph with all negative weight edges halved. So for example, if an edge has weight -2, replace it with -1. The claim is that somehow this makes the task easier in the following sense. The goal now is to either compute the correct negatively single source or negatively shortest paths to each vertex in G prime, the reweighted graph, or if you give up, you're allowed to give up and return a negative weight cycle in G. So one thing I did not talk about so far is that if there's a negative weight cycle in the graph, then distances are infinite because you can just traverse the cycle infinitely many times. So there's a failure condition in negative weight shortest path, which is if there's a negative weight cycle, then you can just declare failure, output a negative weight cycle, and then just imply that distance can be infinite, minus infinity. Okay. So one failure condition we're allowed is to define a negative weight cycle. So why is this task easier? It's because note this graph and this graph are different. Okay, so in some sense, the failure condition is actually easier now, in the sense that G prime may not contain a negative weight cycle, but you're allowed to fail and return one for G. Okay, so there's a gap between these two graphs, which makes it easier. It turns out this is actually one of the key ideas in their paper. This actually does make things easier. But I want to just convince you that this is somewhat an easier task. In the sense it's not a full general like negatively shortest path or negative weight cycle task. These graphs are different, which makes it like there's a gap between them, which makes it easier. Okay. Now suppose we do this. So this is like what I claim will be an easier task. Why this is easier will not all be clear, but we'll see some structure later. But for now, let's show that this is essentially enough to solve the problem up to like another log factor. Here's the idea. Okay, suppose we compute such a potential for G prime. Okay. We want to reweight this graph. Now we know that the G prime is not G itself, so reweighting may not like immediately finish, may not give you non-negative weight cycle, right? But I want to say that you still make some progress. So what is the progress that you made? So consider a negative weight edge in G. After the reweighting, what happens? Well, we know in G prime, the weight is non-negative. So the weight in G prime with the offsets is non-negative. But that's not quite true in G because weights in G are more negative, right? Weight in G prime is the weight half. So like -2 becomes -1. So it's less negative in G prime, more negative in G. So this can still be negative. But how negative? We use by definition, this G prime is the half weight, which means that this, if you just, I guess, increase by another half, you increase here by half. So we know that this new weight is at least the old weight half. So recall, this is a negative weight. We're assuming that this is a negative weight. So the new negative weight is half the old negative weight. Okay. So what does that mean? That means that it's half as negative. But it also means that if you repeat this log n times, you essentially get negative weights like polynomially small. And at this point, you can actually, so now there's like a rounding step where you can assume that because the weights were integers to begin with, if the weights are polynomially small, you can essentially round them to 0. This is what a skip I was skip. But essentially, this is actually the only place we use the fact that the weights are integers. This allows for a rounding step at the end. Are there any questions? Yep.
If weights are integers, what do you do if it's odd?
Great. Yeah, we will still have. So for now we'll still have it. So like -3 becomes -1/5.
Okay.
So you might be asking, well, these are not integers anymore. But it turns out it's true that like so what is true is that there's still a discretization among the shortest path distances. Like there's still like at least one apart. And this will and together with the rounding step means that you can essentially round. So this does require some work, but more or less it's true.
Isn't it like log Wn?
Oh, true. Good. Yes. This actually like the log even n times W. Yeah. I guess you want to go from W down to one over polygon, so n times W. Right. Okay. So there's one final thing I want to talk about. There's one final claim I want to prove about potential functions. This will be useful later on. In fact, this is not the only way to do it, but this is just a good exercise in potential functions that makes it work. Okay, so I claim the following special case is actually easy. So consider a following graph where the following is true. For every vertex v, the shortest SV path contains at most h negative weight edges. So think of h as maybe like polylog n, like pretty small. Of course, this is not true in general. A path can have maybe a path can have only negative edges. So like this is completely false in general. But suppose we have this like structured example where every shortest path in the graph has at most like polylog many negative weight edges. Now there are multiple ways to solve it, but I want to solve in a way that uses potential functions as a way to just understand it better. Okay. And the claim is I can then solve this problem in h times m time, like excluding log factors. Okay, again, there's multiple ways to solve this, but here's a way that uses potential functions. I construct the following new graph. Let's say this is an initial graph. So it's a directed graph. I'll color them as the negative weight edges are going to be red. The non-negative will be black. Okay. I will not really like designate weights themselves. They're not too important in the construction. But it is important to distinguish negative from non-negative. I'm going to duplicate this. So this will have multiple steps. This is not the final construction. I'll duplicate this graph multiple times. In fact, I'll duplicate h plus 1 times. And then I will, instead of remove the negative weight edges within each piece, instead I'll connect them to like across each other in the following sense. For each negative edge, I'll connect the tail vertex from the previous copy to the head vertex of the next copy. So this edge here, I take the tail of this copy and the head of this copy. Essentially, this says that if you take a negative edge, you must jump to the next copy. This is what it's saying. Okay, and I'll do this for all the for every consecutive pair. I will do this construction. This is almost the final construction. I'll do one final step, which is I will add kind of like self edges. These are edges from UI to the same UI on the next copy, the UI plus 1. This is kind of saying I can freely move from the same vertex to the next vertex through the edge of weight 0. Okay, so this allows us for me to like translate from any vertex all the way to the same vertex. But of course, it's more advantageous to use negative weight edges if you can. So this is kind of saying I can go to the next level for free, but perhaps maybe it's more advantageous to use negative weight edges. Okay, so this is a graph. It has h times m edges about. And let's kind of understand why do we construct it this way. So I want to kind of like map original way, paths to paths in this new graph. So here's an example. Suppose I consider this path. Okay, so from these, so there's 2 non-negative and 1 negative edge. I can map this path as follows. I can use the first 2 non-negative edges in the first graph because they're non-negative. And then when I take the negative edge, I'm forced to use to like move to the next graph. Now that means I end at this vertex. Now it's nicer if I end at the final vertex. So actually I'm going to use like at this point I'm going to use these self edges all the way to the end. But these are edges of weight 0, so they do not affect this path. So this is how I'm going to map every path. I'm going to essentially use negative edges when I can. And when I finally stop, I will just take self edges to the end. Here's another example. If I take this path, this has only 2 negative edges. Then I will just use the first negative edge, the second negative edge, and then use self edges. So you can see that this captures all paths with at most h negative edges. Because every time you use a negative edge, you go to the next copy. There's only h plus 1 copies, so you cannot do this forever. But this is okay up to h negative edges. And if we assume this very structured assumption, then this does handle essentially all shortest paths. And finally, I want to just immediately give you a potential function that makes this okay. So first of all, this graph still has negative weight edges. This is like, you cannot just run Dykstra on it. Turns out you almost can. There's other ways to do this, solve this, but for now, let's apply, that's what we want to apply a potential function. I will apply the following potential function. The potential on essentially every vertex on copy I will just be minus I times m, where m is like large enough, like much larger than the largest limit. I'm going to claim this is good. So why is that true? Well, let's consider, well, first of all, edges within a copy, their 5 values are the same on both endpoints. Because everything in the same copy is the same. So edges within the copy are still non-negative because the plus phi u minus phi v does not change anything. What about edges from one copy to the next? Well, for this one, I'm adding phi u1 minus phi u2, v2. Phi u1 is just 1 minus 1 times m. Phi u2 is plus 2 times m. So this is your plus m. And m is large enough, it's bigger than any weighting graph, and therefore it's not negative. So this is just a one simple way to apply a potential function to just like essentially make all edges non-negative in this very short period. Are there any questions?
To be clear, in the last copy, rather than copy the negative edges to the next, you just delete them, which makes it so that within that last copy, the potentials are all the same again. Because if you kept the negative edges there, then you
there's no negative edges in the next copy. Is that what you mean?
Yeah, but you also delete them in that to make it so that there's no negative edges, or else the potential would do nothing for you. Is that right?
So this path is still from the previous. This is from the previous to the.
Yeah.
So it's still like minus h times m plus h plus 1 times m.
Yeah.
So,
Within the last copy, you have no negative edges.
oh, correct. Yeah. There are no negatives within any copy. Yeah.
If you don't add the self edges, can this solve exactly h hop?
Yes, that is true. That is true. Yeah. You don't have self edges. This gives you exactly h. That is true. The one reason why I added self edges is because it's mathematical h. So I'm allowed to just essentially move to the end without incurring any cost. Great. So what is the algorithm? You apply this potential function, run steals over shortest paths. The distances from the start to this final set of vertices gives you the shortest paths. Because this captures essentially all paths away at most h. So this is just one way to apply potential function. Okay. Right. So essentially, all edges are non-negative under this potential, and therefore run Dijkstra on this graph of size h times m. That's right. Okay. Okay. So that's essentially all I'm talking about. All I'm going to talk about with potential functions. Let's continue to the next ideas. So this idea also shows up in this B and W algorithm. Essentially, at a high level, you're going to apply some kind of divide and conquer. So here's the idea. So this is a graph problem. So what does divide and conquer mean for a graph problem? I want to split the graph up into, let's say, 2 pieces. And ideally, they're balanced. If they're balanced, then kind of divide and conquer has nice recursions. I'm going to solve recursively negatively shortest paths on each of the induced pieces. Okay? And what by solve I mean I get the shortest path distances, but then this can be converted to a potential function. Okay. So I'll have 2 recursive potential functions on each piece. And so far this is efficient. Nothing is slowing down. If I can divide into 2 pieces, recursively solve them, then that's fast. That's good for recursion. The hard part is, well, how do I solve negatively shortest paths given this recursive solutions on the original graph? This turned out to be hard. So why is that? Well, here's one thing we do. We have these 2 recursive calls. I've gotten the distances, but in particular potential functions. Let's kind of just merge them to a single potential function. This means that all edges within each piece are non-negative. But edges between the 2 pieces, they have weights, old weight plus phi 1 minus phi 2. There's no relation between these 2. These are independent subproblems. So this can be negative. So this means that this divide and conquer strategy gives you essentially 2 pieces whose induced graphs are non-negative, but things in between are negative. So what does that mean? Well, so here's the ideal scenario. Suppose we kind of divide the graph in a very nice way. Every shortest path, the ideal setting is every shortest path crosses between the 2 parts at most h times. What does that mean? That means that after the reweighting, this path has at most H non-negative edges. And therefore, you can just run we run the special case from the previous slide to solve this. Are there any questions about this? Yeah.
What exactly do you mean by like crisply solving negative weight single source trace path on each side? Like the source is on one side.
Great, right, great. Yeah. So I'm being a little vague here. So more precisely, we'll solve it in the setting where you either think of it as like add a new source with. Actually, in this case, it doesn't really matter. It doesn't really matter. In fact, there's like essentially negative and shortest paths and finite potential. There's equivalent. Right? Given one, you can just do the other. We're just treating it the same problem. If you want to be more precise, you can either pick any source. If you pick any source, this will also work, right? To solve negative and shortest paths, or you can do the construction from before, which is add a new source of weight 0 to everything else. Which is actually this latter is what we'll actually use because it has more structure. But for now, you can just think of it as any source. Okay, so once again, I just want to reiterate, you think of potentials and single source shortest path like they're equivalent. Solving one will solve the other. In fact, in this case, we really are using both variants because we need the potentials here to run single source shortest paths. So the takeaway from this slide is that like essentially the divide and conquer strategy reduces to finding a good partition, a good balanced partition. And by good, I mean the shortest paths do not cross between the partition too many times. Okay. So how are we going to find this balanced partition? This is where we're going to use this more modern tool of graph decompositions. So consider the following graph. Let's define G prime. So we call it G prime is a graph G with like negative weights halved. This will be crucial in this plane, but for now, let's imagine this being some graph. I'm going to replace all negative weight edges by 0. And the reason why I do this is because we know how to find distances in positive weighted graphs. So this is just like saying like we cannot quite like find any notion of distance in a negative weight graph. Let's just replace all negative weights by 0 so that we can like have some notion of distance that we can compute. Okay, so I want to make the following claim. And this is really the key like kind of claim that explains why we're considering this G prime, which is G with negative weights halved. So let's consider the following like scenario. Suppose that this positive weighted graph has diameter at most delta. Okay, so what is diameter? It's just the maximum distance between any pair of vertices in either direction. So for any pair in either direction, find among all such pairs, find the maximum distance. That's diameter. And because this graph is non-negative, this means that this diameter is always positive. Okay. The claim is that if a negative weight path in G prime has a large weight in G prime with non-negative edges, then there's a negative weight cycle in G. So once again, we call that this is G prime, this is G. So there's a gap between these two, and we're going to crucially explode this fact. Okay, so this proof essentially essentially by definition, but let's collect all definitions. So by assumption, this path has weight more than delta in this non-negative graph. This means that the total weight of positive edges exceeds delta. So this is equivalent. Just because like non-negative edges in this graph are 0. They contribute nothing. This is really only the positive edges that count. Okay. This assumption, what does that mean? That means that the total positive, which is a positive number, plus the total negative, which is a negative number, this is total negative in G prime, because it's negative in G prime. This is negative, right? Because the total weight is just the positive plus the negative. Something positive plus something negative. Negative is even more negative, and that's why it's negative. We already know that all positive edges are the total weight of positive exceeds delta, so this is more than delta. The only way for this to be negative is if the negative part is less than minus delta. And here's finally where we use the fact that G prime is G with weights half. This means that it's less than minus 2 delta in G. Okay, this is the crucial implication that we use that results from this definition of G prime. Okay, so we're almost done. So what do we have? We have had a total weight minus delta in G. Why is it minus delta? It's because in G, this is still like something. Let's call it delta maybe. This is like half, this is less than twice of that. Think of this as 2 delta. So if you add them up, you get minus delta. And now finally, we'll use the fact that the diameter is small. So this is just some 2 arbitrary vertices. But since the graph is a small diameter, we can close this path into a cycle the other way. This path can have weight at most delta in this graph, which also implies that it's the same weight in G because G has only smaller weight edges. Because how do we get from G to this graph? We first have negative weight edges. This only increases edge weights. Then we replace negatives by 0. So if we go back to G, this is only smaller. And this goes the cycle. Are there any questions? So far everything I've talked about is really in B and W. So this is like one of the key ideas in B and W. This idea of having edge weights gives you the structure, which is very nice. Okay.
So, I have a question.
Yeah.
What if the graph is not strongly connected?
Great, good question. Right, so in that case, technically the diameter is infinite.
Yeah.
Yeah. So so this is why we're going to run some graph decompositions to make these pieces to have finite diameter, but more precisely for low diameter. So in general, this is like just a completely this claim is too good to be true. Strongly connected graphs have infinite diameter, but the role of graph decompositions is we'll try to force some diameter guarantee. Any questions? Okay. Okay, so what is the role of graph decompositions? So let's begin with, suppose the graph has diameter delta. The role of graph decomposition is that we're going to decompose the graph into, so imagine that delta is like a very large number to begin with, okay, maybe like polynomially large. So we'll begin a very large delta. If the graph is not strongly connected, we can maybe force it to be strongly connected if we really want to, by adding super large weight. Just not too important. So this graph is polynomial diameter, and the idea is we want to kind of halve the diameter in each step. So how do we do that? We're going to run what's called low diameter decomposition. So by the way, this is from the previous work, so this is still randomized algorithm. You run decomposition into a diameter of, let's say, half as large, such that every single edge is cut with probability this quantity. So how should we interpret this? So longer edges are cut with higher probability, right? Which kind of makes sense. If an edge is longer, then maybe like, if an edge is super long, then maybe it just cannot belong to any cluster. But longer edges should be cut with proportionally larger probability. And there's this factor here. Okay, so you can interpret this as saying that the larger your diameter parameter, the less you should be cutting every edge. Because you're decomposing larger diameter pieces. So you should be less likely to cut every single edge. This is almost true. This is true in undirected graphs. For directed graphs, you have to kind of ignore some dag edges. I will not actually talk about this in detail. This is something that BAW did have to address. But this new algorithm, which I will talk about, will not need this fact. So that's why I will not talk about it.
Why do we have the log n?
Oh, right. This is actually a loss factor. So this is actually it's hard to explain, but this is like a kind of a loss. This is an additional loss factor from this decomposition. So this is ideally you replace this with 1. That turns out to be like perfect, but it turns out you cannot quite guarantee perfect decomposition in general graphs. And in fact, this log n is unavoidable. But log n is like kind of small. Just think of log factors as small for the sake of a fast algorithm. Okay. So what was the fact from proof from the last slide? If there's no negative weight cycle in G, then any negative weight path has weight at most delta in this graph. And together with the low diameter guarantee, that means that the expected number of edges cut is like log n. Right? These perfectly cancel. So there's a few steps I'm skipping. The first step is we will use this construction where we add a source vertex with zero weights everywhere. This means that all paths have to be negative, right? All shortest paths have to be negative paths. You can either think of like this supersort construction or just like start anywhere. The point is this start anywhere definition forces shortest paths to be negative if they're not just the empty zero path. So any such shortest path has weight at most this, and therefore this decomposition gives you a small number of expected edges cut. And here's where the other detail I'm skipping is that this is an expectation. This is not deterministically over all shortest paths, and therefore this requires more work. But morally, this is like the idea. So this essentially is like all the ideas behind this B and W algorithm. And I guess in the last 10 minutes I'll discuss how do we get something deterministic. Okay, so here's it. So here's the idea. The idea is I'm essentially going to add some notion of padding to these decompositions. And here's like an ideal setting. Suppose I can find about half the graph, like let's say half number vertices or edges, such that define the padding out of let's say U to be all vertices of distance at most, let's say delta over log squared n. Again, this is just like think of it as like delta over some polylog from the set U. Okay, so in other words, every vertex here is reachable from some node in U with a path of length at most this. This is reachable out. So like from U to here, not the reverse. The direction doesn't matter. And I want this padding to be small in size. So let's say it has a small number of edges or vertices, depending on which level you prefer. So we'll call this a padding. And here's the crucial idea behind this padding. So recall that from this B and W technique, we've essentially narrowed down to all paths of weight at most delta in this non-negative graph. These are the graphs that correspond to shortest paths. It must cross between U and U minus U intersect, and the complement excluding the padding. So this is U and the padding complement. Okay, so how many times can a path go from U to really outside the padding? I want to claim that this cannot do this back and forth too many times. And why is that? That's because how do you even cross from U to outside the padding? You must spend this much distance to even cross from U to outside the padding. Because this padding is defined to be all vertices of this and most this. So the moment you escape the padding, you spend this much distance. Now, because this padding is one directional, it's possible for you to directly go from this side to back to this. This padding is one directional, so edges like this do exist. But of course, you have to go back and forth. So every time you go from left to right, you must spend this much. And if your path has weight this, then you can spend at most logs of lines. Okay, so we're going to do something very similar. We'll recursively compute. But here the catch is now we're going to duplicate this padding on both sides. This will be important, and we'll see later on why. And the reason why the padding must be small is that the padding will be duplicated. This will increase the recursive calls slightly. The total size of recursive calls grows by 1 over log n fraction. And the number of recursive levels is log n, then the total growth is like this, which is 1. So in other words, you just think of this growth as like small enough that because the recursion time is also small, this kind of balances out. Okay, so now suppose we recursively computed these two graphs. Well, once again, kind of a constructed graph where you add these edges in between, because these edges do exist. Once again, these can be possibly negative because what is this edge? It's weighted u plus phi1 of u minus phi2 of v. So these again have no relation, so this can be negative. Note here that vertices are duplicated, so like each vertex is actually duplicated on each side, but that's okay. But once again, we're going to use the how many negative edges can a path contain? Well, every time it goes from U to the outside of the padding, it can use one negative edge. It can maybe in the middle of the padding just take an edge and then go here. Right? So it uses one edge from left to right. Now, of course, from right to left, it can directly go back to U, but that's okay. This is just another edge. Once again, to go from back to right, it must also use another edge. But this back and forth can only happen like log squared times, maybe twice that times. And therefore, any path, shortest path, contains at most like 2 times log squared negative edges. So the previous divide and conquer strategy works. So one remark I want to make is that, so why are we duplicating this padding in both sides? It's because this, it's to kind of handle like shortest paths like this. So shortest path can actually kind of go between U and the padding arbitrary number of times. So this can be arbitrary, like not just log squared. Because there's no, you can kind of go tiny bit into the padding and go back in. This can happen arbitrarily. And the reason why we duplicate the padding is because we want this to be supported on one of the two graphs. In this case, it's supported here. Similarly, if a padding is slightly here, then it's supported here. So only when it crosses, and you're forced to take a negative edge, do we actually use a negative edge. But this can only happen 2 times less times. So any questions about this? So that's essentially the idea. And the remaining step is how do you construct a decomposition. So it's actually kind of, the one line answer is we kind of compute sparse cuts. A distance notion of sparse cuts, if you're familiar with sparse cuts. And here's like a more, here's out in more detail. So let's start with any vertex called S. What we're going to do is we're going to find what's called a sparse ring. You can, if you're familiar with sparse cut, just think of it as a sparse cut of distance at most this is the same parameter we saw before. Okay. So what do I mean by that is, let's start with S. Imagine keeping track of the current ball, and on each step grow this ball by this parameter each time. Okay, and I will stop the growth if the next kind of layer, which you can think of as a ring, is sparse in the following sense. Its kind of mass, either size, the number of vertices or edges, is at most 1/log n times the ball size so far. So essentially, stop when the growth, stop when the next growth of distance delta over log squared barely increases your ball size. And so the classic sparse cut argument is that this cannot happen forever. You cannot keep trying, you cannot keep growing and failing to cut forever. And the argument is if the rings are always not sparse, then every time you add another ring, you grow by a 1/log n fraction, because that's your sparsity guarantee. You cannot do this more than log squared n times, because if you do that, then you grow from 1 all the way to n. Right? So you'll grow by 1/log fraction. After a log n iteration, you grow by constant. at another like log n constant growth, you exceed n, at which point you have to stop. Okay, so this is the just standard sparse cut argument, which says that you cannot grow too much. And that's why I picked log squared in here. So this is actually the reason why this is to balance with this. Okay, so, but we'll talk about later on. So what happens if you just get everything? We'll talk about later on. But now suppose that you don't get everything, you get like a small ball. Then you add like this piece to U and just repeat. So you'll pick a vertex, find a sparse cut. Let's say the ball is small. Then you add this to add this to U. I missed a step, which is you actually delete this from the graph. And then repeat elsewhere. So what is the time you spend? So when you kind of grow a ball, you only need to spend time proportional to the ball size. That's because you run like say Dijkstra on a graph on negative edges. You only like kind of like spend time proportional to what you visit. You can terminate Dijkstra early in that sense. So you spend time proportional to this. You cut it out. And here's why removing is useful, because then you cannot redo work inside work. So every time you find a ball, you cut it out. You spend time proportional to that ball, but then you never revisit these vertices because you cut it out. So more precisely, you work on an induced graph of what's your limits, and you just keep on doing this. More precisely, you cut out the blue region, but not the green region. So keep the green region. But it's okay to do work on the green region because it's like barely as larger than the blue region. You're still spending time proportional to the blue region. Any questions about this? This is like kind of at a very high level.
So you keep going until you get about half the graph.
Kind of, yeah.
That's the blue part, and
Yeah.
the union of the oranges, the greens.
Right, you take the union of everything. I see. So there's a lot of details missing, of course. This is actually not fully general. Let me just talk about a failure case. So what happens if, like the very extreme case, what happens if like the first ball you broke just immediately gets everything? Right? It's possible that like you just immediately get everything. But more generally, suppose the ball just grows too fast. In the sense that, suppose like you find maybe you grow like before you find a sparse cut, you just immediately get everything. This could be possible. This will still happen within log squared iterations, because that was the sparse cut analogy. But it could be that at some point you get everything, and the next level is actually nothing, because there's nothing else to grow. So you get technically get a sparse cut there, but it doesn't really help, because you got everything. You don't want to delete everything, because you want things to be balanced. So let's consider like a very simple case. Suppose you reach everything before, let's say, half the maximum number of steps, like log n squared n over 2 steps. Okay, so this is radius delta over 2, because this is the growth per step, and you're growing for this many steps. So you're growing for like total like radius delta over 2. Okay. Okay. So in that sense, you're actually not like, you're kind of stuck in the sense that you cannot really cut a ball at that step. But here's what the algorithm does instead. What if you try the ball in the other direction? And let's say like the same thing happens. So by this I mean like either reverse of the edge directions or grow the ball in reverse, like your computer ball where like your edges go into the ball. You grow it the other way. If you grow the other direction and also fail, in the sense that you fail to, you get everything before this many steps, then you also get that every vertex has distance at most delta over 2 to that vertex. Together with distance the other way, this essentially gives a diameter delta over 2. I think I failed with the parameters here. This might be this is probably delta over 4, so you can multiply by 2. But these are just constants. You can kind of fudge them however you want. Like this is just probably 4 here. So the point is like the failure condition kind of gives you a small diameter piece. So if you fail to grow the ball in both directions, then like you kind of have a small diameter piece, which is also progress, because the goal is to have the delta. So what I'm saying here about the finite balance decomposition is actually not quite true. There's another failure case, which is either the entire thing is like just diameter delta over 2, or maybe a large part of it, potentially much more than half of it is delta T2, which is still progress because the delta drops. Maybe the size doesn't drop, but the delta drops. So you kind of still make progress in that case. Of course, these are like, there's a lot more details. There's maybe 3 more pages of details. Which is that, like, technically you kind of have to grow in both directions. So the failure condition is that both directions like essentially get everything. But that means that the success needs to be like one direction gives you a small ball. So really what the algorithm does is like it tries to grow a ball in both directions, like in parallel. And then if one finds a small ball, then terminate the one immediately. If you grow them in parallel, you kind of spend time proportional to whatever the smaller ball is. So you're still like okay. And then you cut that ball, whether it's an out ball or an in ball. And then you kind of repeat this, like just choose another vertex, do the same. And after some point, either the total in ball size or total out ball size maybe exceeds like 1/4 or something, at which point you have a balanced partition. And finally, at any step of the process, maybe you have a failure condition where both balls run to completion, or by run to completion, you like maybe exceed like half the vertices. In which case, you can extract a large piece of diameter delta. So that's basically it. So this decomposition itself runs in essentially Dijkstra time, like with no log factors. This is very elementary. But where you do pick up log factors is like because it's like sorted in here, and the fact that you have a dividing carbon. So it does pick up like I think 3 log factors beyond Dijkstra. Actually 4 if you add the scaling, the like halving and negative weights log integers. The total number of log factors is like 4, which is like reasonable. But I guess open, can you actually reduce more log factors? Because ideally we want something like 1 or 2 logs, which would be like potentially practical. So I think that's all I had. Thanks very much.